Hi guys, today I want to continue chemistry with the concentration effect on electropotentials. Okay, as we can see here, this part here, right? Concentration, this part here. Red color, concentration, okay. So I've started with you already. So we go into more kind of examples and also to use this equation here more readily. And it happens quite a lot in quite recent 2018, 2019 questions. So let's go straight ahead to that, okay? So here we are. Now this is the question come from 17 February, all right? Very simple question. It says the electropotential. Now this means that you must understand the E naught here, or E standard here, right, is for 1 molar, 1.00 molar for your ions, which is a nickel 2 plus. Okay, so is this one here, right? Which means if I write it in this way, this would be the reduction from this is the correct one. So always in reduction, okay, plus going here is reduction. All right, remember always reduction. So that this E naught here will be always reductions not here. Okay, so this is the original E naught you get from the table. So you always refer to this E naught value. Don't go and reverse it. All right. So state explain how the electric potential. This is actually your standard potential. Okay, changes if the concentration is decreased. So basically, the Charles principle now is 1 molar here. This is the value here. Now, if it's a 0.1 molar, so of course, you're going to shift backwards now, okay? Shift backwards means going backwards is more negative. So E becomes what? No more, becomes what? More negative. You go back faster, go more negative. Okay? Why? Because equilibrium position. Position shifts where? Shifts backwards. Shifts backwards, or you can say, okay, shifts to the left, Okay, let's for 1 mark only. Let's see how the answer is here. All right, potential, electropotential becomes more negative. It's going to shift left, right? Shift left or shift backwards. Okay, so this is the easy one to explain. Concentration factor. Now, next one, of course, it gives you E naught. E naught again is for what? 1.0 mole per dm cube for this one's for both of them, you know. Okay, is 0.141 minus, right? That means this in reduction form, right? This is the correct E naught value. Okay, always refer to this E naught value. I cannot emphasize it more because in exams, the marking symbol according to the E naught values in the data book, not to yours, shift left or shift right. Okay, now. So calculate electric potential is not standard anymore when this is this concentration, this concentration. Okay, it means this half cell. Okay, this is the half cell here, right? Of course, with your platinum here. And of course, this solution here contains no longer 1 molar, but Cr3 plus, how much? 0.60, all right, moles per dm cube. And here, Cr2 plus, how much? 0.15 molar per dm cube. Okay, now. Okay, so I want to talk about this one only with no reference here. Okay, of course, it's reference to hydrogen, but don't care about that. So you quote this one here, this Nernst equation, right? Oxidized species, which is the more positive one, over the reduced species, which is the negative, less positive. Of course, this is oxidized, this is reduced one. Okay, so this one over this one here, so quite simple. Right, you just put it, just solve it. Now the Z here is the number of electron transfer. So here's 1, so the Z equals to 1. Okay, sometimes they put 0.059, sometimes they put 0.06 as well. Here 0.060. Okay, so depends on the question, but normally it's 0.059 to be exact, right? So quite simple. Of course, if this is 1 over 1 here, log 1 over 1 is 1, log base 10 1 is what? Is 0. Right? Okay, so this is 0. That means this is equal to E naught value. Okay, now so here, what's the answer? You can see here, very simple. They just put the ratio here, which is 4.0, which is correct. Right now, okay, which is 0.4, sorry, right? And then of course you just solve it by using log. You better know how to use a log for calculation. Okay, so practice it. I'm not going to do it here. Okay, So this is the value here, right? So it's still minus because right, it's the half cell, minus 0.37. Okay. And next one, of course, here is a bit tricky one here. All right. See, some of this we don't use it one, but it comes out in a very sneaky way. So now this, of course, we'll do later when you do it in electrochemistry. I won't teach you now. So use standard electric potential E again is for your normal one, for the standard one. Okay, from data board to calculate the E cell against standard for the foreign reaction. Now this is the overall reaction. It's the overall. You must understand the question. That means it's the redox reaction. That means there are two half cells involved here. Okay, they ask you for the cells, two half cells involved here. Okay, now how do you figure it out? First of all, you see down here chlorine, right? And so that means one of them must be, well, chlorine here. Here we chlorine, and here's your Cl minus one. Okay. Now the other one here, you have to decide. Now this figure here is quite common, but you hardly use it. Okay. So if you look at your data booklet, right? ClO minus and OH minus, these two figures are there. Okay, and of course this fellow here you can see later. So what are some of the chances of seeing here? So you can see now, here, this one here. I'm going to, okay, blue color, okay. So you can see ClO minus, with OH minus. Now there's another Cl minus. So this one here. So chlorine is going to go forward. This is forward here, and this is going to go backwards now. Yeah? Because chlorine is on this side, it means chlorine is undergoing what? Reduction. Okay, so you can see here, so you must use your same properties of brains properly. Okay, so Cl is on this side, so it's going here. Okay, so this is the first one. Okay, which means the other one, of course, with OH, right? OH going the other side. OH and your Cl minus, which is this one here. See? So here. Okay, now this is OH going backwards. Right, so here, blue color, see, right now this is the original. Okay, so this one here is going this way. Right, so I put this one forward first because chlorine is over here. It's plus 1.36. Here, now I go backwards. I write the other way, Cl minus plus 2 OH minus, give this one here, and I reverse the sign. Now here I do it the same, but I reverse the sign plus now. Okay, so you can see here, this one is minus this one here. Right? Okay, right? 2 here or minus 1 of the thing here. Okay, right? So what's left behind of Cl2 plus 2 OH minus, right? Give you Cl minus here, and this ClO minus here, and plus water here, which is this equation. See, you give nicely on this. This is the overall equation. It's not. And of course, your E cell just plus. Okay, or you can use this method here. As I said, if you don't want to change the sign here, use the method. Okay, E cell goes to E redox, reduction minus E oxidation. So it's reduction of cost, okay, right, which is not original, right? And of course, oxidation, this one here, the original is positive now, okay? So it's positive here, okay? And you get this answer here, okay? So this is the E cell, you can see here it's plus 0.47, plus 0.47 here, 0.47, okay? They don't care about this, but better always add plus one, otherwise cannot. Okay? Now, the other one, of course, is a concentration effect. See, the OH minus, now according to this one here, see, for this inert value, the concentration of this is what? 1 molar, 1.0 mole per dm cube. Similar, this also 1.0 mole per dm cube. Okay? Also similar, this also 1.0 mole per dm cube. Okay, so when they say, well, when OH minus concentration is increased, right? That means it's going to go to, let's say, 5 molar. Okay? 5.0 mole per dm cube. What happened? Okay? And the E cell, remember the E cells here, there's no more the standards. So this one is, that means no more standard was measured. Indicate how the E cell will compare to E original, which is a standard. Okay, but put a tick in the table. So now look at this. This is the easiest to look at. So this according to this equation here, for this value here, this is 1 molar. Right? So if you increase this one here, is increased to let's say 5 molar, you will shift forward, according to the Shortest principle, shift forward. If you shift forward more, it means it's more visible. It means it becomes more positive. Okay, become more positive. So more positive. So which is more positive here, right? Becomes more positive now. Okay, more positive. Okay, so this concentration factor effect you can see here. Okay, right. Box 3 tick. The shortest argument, more OH minus concentration equilibrium shift to the right. Okay, to the right or forward. Okay, so they use right and left more often. Okay, so that one mark. Now this one here, I just want to show you here. This one actually is a form lower 6 question, but they give it now in the cell form. Now, very important because it's a redox reaction. You must understand all is a redox reaction. A half equation, okay, half equation involves bromate. You learn this more in your A2, bromate BrO3 minus and bromate ion shown. Now this is the half, okay, half cell. It's not in your data bullet, but they give it to you. Okay, so this is going this way, right? Reduction. Okay, this is the original E0 value. And alkali means the OH minus of chromate. Chlorate. Again, a ClO minus. So this is a very common one coming up. This is a powerful oxidizing agent. Will oxidize bromide. It means it will go backwards now. Bromide to here. That means you're saying that this further here will go this way. So you rewrite the whole thing here, right? This way. So Br minus here plus OH minus blah blah blah, and you change the sign here. If right, do by this way now, okay? Right? So then your chlorate. Okay, chlorate here in alkali solution, right? So chlorate here, what kind of reaction is it? This is the only one you see in your data booklet. You can check it out here. Go over the data bullet, ClO minus, the only one here that can undergoes what? Reduction to accept electron from where? From your Br minus. Okay, so this is only one on the side, no more. So use this equation. See now, so the choice of equation is very important to know what to choose. Okay, so now this is the, I copied down here. So ClO minus plus H2O plus 2 electrons, use Cl minus, OH minus, and so forth. Use one is plus 0.869. So now to balance up the electrons here, this is 6 electrons, so times by 3. So 3, here is 6, 3, and here is 6. Don't times this, this is the same. Why? Because it's 1 molar for all of them. Okay, so you cancel off water, 3 water. Cancel off here 6 electrons, right? So this 2, the 6 here, you cancel off 6. So what's that behind is this one here, Br minus, 3 of this here, 1 of this BrO3 minus, and 3 of this one here. Okay, right? So they ask you use the blah blah blah. Okay, write an equation for this reaction. That means this one here. Okay, calculate the E cell. Very simple. This one here. So you get kill 2 birds with 1 stone now. Okay, so you can see the answer here. Right? It's the answer here. Where is it? Here. 1 Br minus and 3 ClO minus. 1 Br minus and 3 Cl minus. Go to 1 BrO minus and 3 Cl minus. Okay, right. Okay, EMF plus 0.31 plus 0.31. Okay, so I'm just going this through with you. Right, now I won't go this one with you here. It's okay. You can this one you can do later by yourself. I got no time for that. Okay, now let's say another one here. Here. Okay, now this is another good one. Remember, now they combine the whole thing, the whole cell with concentration effect. Okay, and also with Nernst equation. So you see the whole question evolves around all the syllabus. So here is an electrochemical cell. Remember, it's a cell that means contain 2 half cells. It's contained with 2 half cells. Okay, so SN4 plus SN2 plus, they tell you it's not SN solid. Okay, right? So it's this further here. So I just put down here. Now remember, I wrote original. Okay, original is reduction form. Going this way, reduction. Okay, right? Aluminium. Okay, also reduction form. Right? So I put down here. Just I don't want to refer up and down now. So when I draw a cell, it's like this. Okay, for tin and 2 plus and 4 plus here is both 1 molar. And this, of course, platinum. Here, of course, salt bridge and work metal. Here, of your electrochemistry, and of course, this aluminum metal. So this cell is set up here. So state the materials for electrode half cell. Of course, this is platinum, and this will be this aluminum. Quite simple. Okay. So remember, you look at this fellow here. This minus is positive. Of course, aluminum will be negative. Tin will be positive. Or electrons will travel from here to here. This will undergo oxidation. This will undergo reduction. Very simple thing. So once you know how to use the data build-up for the electric potential, no problem. Okay. So here, cell is operated at 298. Why? Because it's standard one. Okay, at 25 degrees centigrade. Right. So Al3 plus here standard, which means this one is what? 1.00 mole per dm cube. See, very important because all this will tell you what value to use as an E naught. See? So this one here, SN4 plus is got this one here. See, different thing. So it's no longer 1. So use the Nernst equation, to calculate the potential for this unknown. Now here they don't give you the Nernst equation, which means you must memorize it. No choice. So E here, remember, there's no more. That means this one is for a different concentration other than 1.00. So now this original one is this is standard one, plus this, of course, standard one for what? For this one. Okay, right? Now I put 0.059. You put 0.6, they shouldn't bother you, but 0.059 better over Z. Z is the number of electrons transfer. Of course, here, how many electrons transfer? 2, isn't it? SN4, SN2, so it's 2 electrons here. It's 2. It's like 2 here. Log oxidized form with SN4 plus, which is this one here, and SN2 plus is here. Okay. So again, this whole thing is a mathematical calculation supernova. Make sure you know how to use now this base log 10. Please remember this again. Make sure you know how to use your log tables. Okay, or your calculator with log. Okay. So this 0.159, you can calculate, or 0.16 the answer is. Okay. So you can see here the answer here. Just a minute. Okay. See. Either way, you get correct. Positive, of course. Minimum 2 significant figures can. Okay, so 0.2. Okay, so now the second part is concentration effect. See, okay, calculation under these conditions, of course. Now here, sorry, now here. Now this is the new. This is This is your electric potential for what? For SN4 plus 2 electrons here. SN2 plus. It's an E. No longer standard, okay? It's plus 0.16, okay? Okay. So under these conditions, it means these conditions here. What is the E cell? Remember, reduction minus oxidation. What am I doing? Okay. So who is undergoing reduction? Very simple. Right now here. Okay. So tin undergo reduction now. Okay. Okay. Tin. So put tin first. So this is the tin one. Okay, original, right now, in the reduction form, plus 0.16 plus, okay, minus, okay, now your oxidation is what? It's aluminum, see? What's the original one? Minus 1.66. So make sure you put minus 1.66, okay, minus 1.66. So you minus plus, so you get plus 1.82, see, 1.82, 1.82, minimum 3 6 figures. Okay, 1 mark. Of course, they ask you for the overall equation, which is very simple. Okay, overall equation. So you must know who is negative, is positive, because here aluminum is negative now. Okay, negative. Why? Because here is negative. Right, so negative. That means it's going to be an electron donor. So it must be going this way, isn't it? Right, to electrons. So it's Al going to this one here. Okay, right, 3. Don't forget the blue first. And tin will be undergoing what? Reductions in, right? SN4 plus. So since here is 2 and 3 electrons, you make it 6. 7 times 2, 2, 6 times 3, 3, 6. Okay, so this one can cancel. So this will be 2 Al, 3 SN4 plus, and some 3 blah blah blah. And so this answer here. Okay, species on mark, balance on mark. Okay, so you see how concentration effect the whole thing comes in. Okay, now another one. I'm going quite fast here because it's quite obvious one of this question. So the whole experience, right? So electrochemical cell is kind of 2 half cells. Of course, you can draw it up if you want to. Okay, I'll just quickly do it for you. I should draw it earlier. Okay, so it's both platinum here. Okay, connect to the voltage here. Of course, this is a salt bridge, and of course, this is a solution here. Okay, PT and this PT. I ask you for PT here. Here you must put your bromine gas, okay? Inward here, Br2, 1 atmosphere. Here's your Br minus, okay, which is 1 mole per dm cube, okay? Right, here's your PT and here's your Mn, 2 plus and Mn, 3 plus, both of them, 1.0 mole per dm cube, okay, quickly, yeah? Right, so this is the whole thing here. Of course, I wrote this down here for me to easily explain. Right, so both and reduction rate is the original inert value. So which is more positive? Of course, magnesium is more positive. So it's positive here. Br is negative now. Okay. So negative means what? Electrons coming out, okay? So negative, so electrons trying from here. Okay. So that means it's going this way. So Br here, electrons coming out this way. Okay, electron is negative, is positive. Okay. So if a diagram help you, draw a diagram. Right. So they say, oh, Br2 and Br minus is standard. 3 plus and 2 plus, of course, is different. So use the Nernst equation again. Same pattern as the other one, right? So find the Nernst equation for the Mn3 plus, Mn2 plus, right? So here, right? This is standard here. 1.+149, see here. Okay, yeah. This is original, raw one, plus 1.49, plus, of course, 2.5K. And of course, it's the oxidized over, it's oxidized over the reduced, okay, concentration, okay? So you can put it down here. Again, solve again, this, okay. Right? Okay? So you can see that it moves, if you increase that, you move forward, okay? Move forward more, okay? All right, so now, again, you can do the equation out, or you can, don't have to do equation and use on that. So which is undergo reduction? Of course, your what? Your Mn3 plus now. So this is 1.53. Yeah. Reduction, this is oxidation. I put wrong again. Okay, which is your bromine. Okay. So plus 1.00. So minus this answer. Okay. Again, they ask you to balance off the equation. Right? So remember Br minus plus is negative, it will go this way now. Negative, go this way. Right? So 2 Br minus becomes, so yeah, this is your reduction. Yeah, right? So you can see you need 2 electrons here times 2 cancel off this equation here. 2, 2, 1, 2. 2, 2. So, okay. Here, say marking is also wrong. Right? 2 here. Okay. All right. So we finish. Last two. Okay. So the time to do, I plan to do the battery with you today. All right, now here again, this is your lower 6 thing about redox reaction, balancing electrons and blah, blah, blah. So they say chlorate, again, chlorate, ClO and ClO3 very common. You can see this very common in your inorganic chemistry, okay? Reduction of chlorate 5 means this is +5. So chlorine here with SO2 forms chlorine dioxide. They tell you, it means this is the reagent, this is the product. They tell you already. So because you don't know all this chemistry, you see, so they tell you. Okay, so that means with sulfur dioxide, means these two are the reactants. Remember this. That means on this side, these are the reactants. You must understand this. This is what they will tell you because you don't know anything about. Okay, and chlorine dioxide, and this one is the products. Okay, so you with this in mind, production, then you need to balance off. Very simple. So how to balance the equation? Redox reaction. Because it's a redox reaction, so you can first of all find what is the, I'm going to use red color here. Okay, you need to find what is the oxidation states. Sulfur, O is -2, so it's 0, this is +4. Sulfur is not, okay? Sulfate here is what's +6, okay? Because the whole thing is -2, right? Oxygen is -2, is -8, 2 is +6, okay? So from +4 to +6, it must have undergo oxidation, it loses 2 electrons. So 2 electrons here must be taken in by your ClO3 minus. So now the Cl here is +5. They tell you already is +5 here, but you can work it out. The whole thing is -1, oxygen is -2. Okay, so of course it's +5. Okay, right? Now this one here, the whole thing is 0. This is -2. Here's +4. So from +5 to +4, it must have gained 1 electron. But this fellow here, 1 more give 2 electrons. That means 2 moles times 2 here. So put 2 here. So everything is ngam times 2. So now this is the answer now. Construct equation for this reaction. Which one? This is the redox reaction. So now this is the AS. AS come together with A2. Right? You can see here the answer. Okay, see now. Okay, 2, 1, 2, 1. Okay, 1 to 1. See? 2, 1, 2, 1. Okay, now here. Of course, now here is another one. Now this is also an AS question. Okay, disproportionation. You will learn later in A2. This one here. See, chlorine dioxide, blah, 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 is on here. Disproportionate. It means that it can undergo redox and reduction at the same time. No, okay, it's like a amphoteric, just as in base of deal. Okay, but this is not, it's not amphoteric, it's oxidizing agent and reducing agent both at the same time. It can perform that. Okay, so with alkali to form mixture of these two. These two must be the products. You know. Okay, so again, you work out the oxygen states. I put blue colors, you can see clearly. I just did the first one here. So the whole thing here is 0. So oxygen is -2. This is +4 for chlorine. Yeah, +4. This, of course, is 1 minus here. Oxygen -2 is -4. This is +3 for here. Here is total is -1. Is 3 here, -2, -6 is +5. So -4 +4 goes to +5. You must have lost 1 electron. Okay. So +4 goes to +3. That means you must have gained electron. So gain 1, lose 1. So 2 lah. See now. Okay. So use this to explain what I mean by disproportionation. That means the Cl +4 becomes what? Cl +3 in ClO2, right? And Cl +4 becomes what? Cl +5 in ClO3 minus. You can see here. Okay. Okay. Cl gets both oxidized and reduced. Okay. And +4 to +5, +4. So as long as you say it goes to here. Right? Explain both, it undergoes both oxygen reduction at the same time. Okay? And then of course they ask you to use it as a cell. Here. Deduce the half ionic equations for reaction B1. Okay, here. Okay, here. So what are the half ionic reaction? Okay, which means you need to look at it carefully here. Right. Now from here, this one I think for this first again, this one here. Right? Both of them start with the same one. Both of them start with +4. So the first one, of course, is going from here, right, to +1 electron to here. Notice, guys, notice here is 1 minus. Notice there's no hydrogen involved, right? So 1 chlorine, 2 oxygen, 2 chlorine, only electrons. So same, here same. So I don't put any OH here or whatever, water, I don't put, okay? It's +1 electron, okay? So this, of course, +4 is your, what? What is minus is 4, is +3. Okay, so it's 1 electron, right? So the half equation. The other, of course, is, see, for this one here, right, to go to this one here, right? So 3, here are 2 only, so one more oxygen. So I need to include this one here. Okay, so I put the 2 OH remainder here to go to here, right? So I get ClO plus, of course, here get water lah. So the balance off. Okay, so the electrons will be plus here. Okay, so you're gonna figure out, because this they don't give you in your data booklet, so you figure it out yourself. Okay, half equations here. Okay, this is a marking scheme here. All right. Okay. This one here. No. This one here. This one. Yeah. So here there is no hydrogen or whatever. This one here. There's a. Okay. Run it off. Can you see clearly? I'm looking at the time actually because I want to start with your batteries really. Okay. See. All right. Okay. Now, lithium batteries, later we'll talk about it also, but now here, see, it comes together. It's rechargeable. It's lithium iodide. Lithium iodine, electrochemical cell can use the general highest heart pacemaker, right? You got a heart is, beat too fast or beat too slow or don't beat at all, whatever. You use a lithium thing, okay? Lithium immersed in boiler liquids. It means it must be wet. So lithium oxidized and iodine. Now they tell you actually what's happening, but you don't have to know. Why? Okay, now use the data to write half equation for this reaction to this two electrodes here. Okay, now these are the two raw ones I got from the detailed booklet. Remember, lithium is always, you write always in this way here, reduction. I cannot exercise enough. Okay, right? So iodine. Now, in this case here, negative positive. So who is if this is a cell, who will be negative electrode? Of course, lithium now more negative than it's positive. It means if negative, it means that you move it side. Okay, right now. It will here from here electron flow. That means you must be given electrons. So this one here, see, right? So I change the sign here for this method. So iodine will accept electrons here to go here. Okay, so the overall equation here minus this is this one here. Simple, isn't it? So you just add up, give it this one here. Later they ask why is it less than plus 3.58? Because of course the thing, see the for it to go from here to here, this one must become gas, so it accepts energy to change states. Okay, right? Now this last one here. Okay, this came out last year, February time. Okay, use the standard electric potential data E cell again for this reaction. Now they give you this reaction. This is the overall equation, overall redox equation. That means one of them is a half cell, the other is another half cell. Of course, this fellow here. See? Now, iodine is 1 minus, this is also 1 minus. So from here to here, only 4 of them, only 2 of them will undergo oxidation. Okay? Minus to 0, so it's oxidation. Let me say lose electrons. Okay, copper 2 plus to 1 plus here, plus 1 here, here will gain electrons. Okay, so now so what are you going to use? See, use a copper 2 plus to 1 plus. Okay, now look at your data booklet. All right, copper. So here you need to see copper 1 plus to copper do 1, copper 2 plus to copper do 1, copper 2 plus to copper 1 plus. Yeah. Okay, so now this is the raw one. Okay, plus 1.5 plus 0.15. Sorry. Okay, see here. Okay, iodine I got here is this one here. So now in this case here, who is negative, who is positive? Who undergo reduction, undergo oxidation? Of course, this is more positive, right? So this will be minus, positive. Okay, of course, electron will move from here to here. Yes, so you have to see the whole thing in perspective. Write all these things down first. Write all these equations down first. Okay, so you can see negative pole and positive pole. That means if this way, that means copper this one is going this side now. Okay, right. So who is undergoing reduction? Of course, this one. Okay, iodine is in, right? Okay, wait, am I correct? Correct. Okay, wait. Now I made a mistake. Okay, see this. I made a mistake here. Sorry about this. I just spotted it. Okay, okay. Now, according to the equation, right? According to the equation, yeah, Cu2 plus is going to C1 plus. I thought it was the other way. That means if this is going this way, right? Accepting electrons, this must be positive. Okay, according to this equation, that means that iodide is going this way. Okay, it's going this way, right? That means this one here will be positive. Okay, accept electrons. This one will be negative. Okay, so this will be reduction. This will be oxidation. I know. Okay, so reduction is this one here. So they say this is the case. Okay, this is the case. This is the case, right? According to the equation, which means it wouldn't happen actually. So if this is the case here, this one plus. This is right. This one here. Okay, minus original here. So you put out here in minus 0.54 and plus 0.15. How much is it? You carry 1 here is 9, so it's 3. So it's minus now, minus. So it's minus now. So you must look at the equation, okay? Right? For this reaction means that if you correct to this reaction means it's not possible. Okay, it's not possible. Okay, minus 1 here. So calculate here, negative. That's right, not feasible to say here. Right, negative here now. So you must have positive 1 for cell. So since negative reaction is not likely to occur. Okay, understand? All right. Now this one here is a Nernst equation here. You want to see is here. Okay, okay. An experiment I put here. I didn't print it because I forgot to print it. So I saw it. I better tell you if you want to. I can't do it. Right here in the experiment, I minus was added to copper 2 plus. The reaction does occur. Right, and a specific sparingly and so on. It does occur, no, right? Now the concentration is blah 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 blah. Okay, calculate the potential. Okay, on the half cell here. Now, so if you look at it carefully here, not this one here. I say, okay, right? So, okay, so use Nernst equation and solve the whole thing here. Can? All right. So here you can see this value here is 0.5 here. Okay, right? Okay, right? So E is very negative and so forth, so forth. Right now, so this is a Nernst equation. Okay, now I finished all the Nernst equation thing already. Now let's go on to here on batteries. Okay, I want to show you what I intend to do today. Yeah, where is it? Not here. Okay, reverse here. No, here. Okay. Now the second part here. I've got about 20 minutes, okay, to try to finish my batteries and fuel cells. Okay, so now this is all general cell, okay? You do the lab one, but this is batteries. It means you use in the house, okay? Fuel cells you use in rockets or use in big companies, okay, where you actually must keep a consistent voltage because TME could suddenly was up, and the whole thing died down. The factory cannot. So fuel cells are like they use in rockets, okay, to provide a constant supply. It means that as long as there's hydrogen, oxygen there, you can no problem of getting the voltage. You are sure to get the voltage. Okay, you don't depend on the hydroelectric power. Okay, state possible advantages of developing other types of cells. Okay, I mean it's fuel cells here. I mentioned them you already fuel cells: nickel metal hydride, lithium ion, and rechargeable batteries. Okay, I'm going to also tell you the dry cell, which is you did in Form 5 or SPM. You do it dry cell. Now let's quickly go to this game. But 20 minutes to go, and I'll try to finish as much as we can. Okay, now this is called the Levante cell or dry cell. Very simply, it used to come out last time in the olden days. Find the E naught value and so forth, so forth. Now this Levante cell is quite special. It's a zinc, made of zinc. Okay, put zinc here. Okay, zinc, right? The zinc casing, right here. This is a zinc casing. Okay, here. See here, down here, zinc metal, right? And of course, then this is the carbon rod. See carbon rod. The carbon rod is unreactive actually, and then this one here is a mixture. It's a mixture of powdered carbon and manganese oxide. Okay, it's MnO2. The carbon powder is as long as it provides a larger surface area for the carbon as well. Okay. Now here is a paste. All these are paste, no, right? These are all paste. Okay, paste here. Why? Because paste. Okay. Because then they are like semi-liquid, they can conduct, the ions can move. So here's ammonium chloride and also plus zinc chloride as well. Okay, why? Because zinc and zinc 2 plasma. Now, okay, now there's a reason. Now there are actually there are 3 reacting substances. One, of course, is zinc, which is very powerful. It acts as an electron donor, right? It undergoes oxidation. It will be a reducing agent. Okay, it will supply reducing agent. It will supply electrons. Okay, whereas this one here, ammonium and of course manganese here will be reduced. Okay, your oxidizing agent. These 2 here. Okay, Now, normally they will only give you either this or this, but you look at American books, they give both, you know. So I'm going to show you, okay, here. Now, so as when we connect here, electron will flow from a zinc. This is zinc, okay? Zinc. That means zinc will become Zn 2 plus 2 electrons. Okay, come in. Okay, and go into here. That means electron will go out here. Okay, you can go to the website and see all these reactions. Okay, so you can see zinc chloride with ammonium chloride. Okay, MnO2 with graph, powdered carbon. Okay. Okay. Now let's look at the whole thing here. So what happens? Of course, zinc. Okay, they must give you because this one here, right? This one here is not found in your data booklet. They have to give it to you. So zinc becomes Zn2 plus here. Of course, this one is given in your data booklet. You can see here the last one, zinc. Okay, right? Okay. Okay, going this way, of course, will be plus 0.76. It's quite high, isn't it? Okay, 0.76, 0.76, 0.7. I'm trying to find it. I see, where is it now? Okay, 0.76 now. Okay, that means it's undergoing oxidation. Okay, I change the sign here. Now, this is for negative electrode now, because it's supplying electrons now. Okay, negative. Now, the positive electrode, of course, it will be, see from here, right? The electron come here, we see electrons now. They either give you ammonium or they give you manganese dioxide. Right? Or can give you both, I don't know now. So if they give you some here, you have to say, well, ammonium ion plus 2 electrons to give you ammonia. They will tell you this now. Okay, and this is assuming 0.74, okay, positive. Okay. Right? So now you combine these two together. Okay, you cancel 2 electrons. Right? You get zinc plus ammonium ion, we come from ammonium chloride. From ammonium chloride here. You can see here ammonium chloride. Okay, this is ammonium chloride. Okay, ammonium chloride. Okay, ammonium chloride. Okay, so ammonium ion will be reduced to ammonia and hydrogen. Actually, it's a hydrogen. The H plus here that's changed to H0. You know. So you get 2 gases here now, ammonia gas and of course hydrogen gas. That's why when your battery leaks, when the zinc become thinner and thinner, okay, and then all batteries will leak, right? They leak. That's why, because zinc no more, they get oxidized now. So of course, why is there water? Now because hydrogen here, right? They have to take care of hydrogen, right? Because ammonia is very soluble, can dissolve in the paste. Hydrogen will explode, you know. So hydrogen will react with this further here, with the MnO2 here, to form H2O. That's why it becomes watery, right? So this one here, percent give water, okay? And now manganese something, right? So this will give a total of how much? Plus 1.5 volt. That's why your dry cell, your ever ready, your whatever ready, okay, is 1.5 voltage. Now sometimes they may give you MnO2 as well. Actually, these two happen at the same time, right? Okay, to boost the voltage. But very hard to give you 2, no? I mean, both of them undergo reduction. Okay, so the other give you one is or this one here. So now if this was given here, MnO2 will plus water plus 2 plus here. Now Mn here is plus 4. It goes to here plus 3 because it's minus 1, this is minus 2 now. Okay, so it's plus 3. So from here to here, they accept 1 electron. So 2 of them accept 2 electrons, okay? Because zinc give 2 electrons. So we put here the same as this, okay, same as this. So again, they give you 1.5 volts. So either way, right? Either way, the voltage is 1. This is called a dry cell, okay? It cannot be recharged, right? Now let's look at the lead acid accumulator. This is a rechargeable car battery, right? So this is a car battery here, okay? It's 12 volts. Why 12 volts? Because there are actually 6 cells here, 6 cells. So 1 cell is about 2 volts. So times 6 is 12 volts. Okay. So what does contain of? It contains 2. Just draw 1 cell here. Okay. So it contains here. Okay. Normally they put in the same place just to make easy. Okay. Right. This is lead Pb, and this is on the surface only. Okay. On the surface here. It's a layer of lead oxide, lead 4 oxide PbO2. This is actually a partially covalent substance. it's a very thin layer, okay, not very stable. So it must be so because it is rechargeable. Ma. So you connect these two together by a voltmeter here, okay. This is, okay, let's say here is, actually you put sulfuric acid one, okay. Let's say it's water first, okay, right, water first here. So under this context here, you can see from the data booklet, right, lead. Okay, there are a few, there are three, 1, 2, 3, lead with lead 2 plus, okay. Lead 2 plus with lead 4 plus iron. This is not what I want, this is not what we want. Lead, see now, lead 4 oxide, this lead 4 plus 4. Lead 4 oxide with lead 2 plus. Okay, so these are the two we want. This one, this one. Okay, so what happened is, remember this plus. So let's say I got here, all right, lead, all right, here. Because no space, okay. All right, let's put that water, okay, we don't care. Okay, this is a volt, the voltmeter. Now this lead PB, and this on surface here only. Inside here is actually lead, no. But on surface here is lead 4 oxide. Okay, it's PbO2. It's water here. So under this thing here, of course, you know, they say, okay, there actually can be Pb2 plus here. Okay, put some Pb2 plus here. Okay, okay, 1 molar. Actually, in reality, it's not Pb2 plus. Actually, it's sulfuric acid. Now, mind. Okay, let's say it is so. Okay, now in this case here, remember, this is the one we want, and this is the one we want. So who is negative, who is positive? This is negative, it's positive. So lead here is negative, is positive. So electrons will travel from here to here. So what's the direction? Negative pole will be Pb going to what? Pb 2 plus now. Yes, not. Okay, which is this going this way. Okay, this way, which is will be plus 0.13. This E. Okay, volt. Okay, but now the positive end going from here to here, right? That means electrons with this one here. So it's PbO2 plus 4H plus, right? That means here also got acid H plus. Okay, H plus here plus 2 electrons. Sorry, here is plus 2 electrons. I forgot. Okay, to give you what? Pb2 plus. Why? 4 plus. Good, 2 plus except electrons. Okay, it's 2 plus here. Hurry, hurry, hurry. Okay, this is what you do for me. Hurry. Okay, 2 plus. Nice, very nice. Okay, 2 plus plus what? Plus water. Okay, plus water plus H2O. And how much is it? Positive, very big, no, 1.69. Okay, overall reaction. All right. Okay, so Pb plus PbO2 plus 4 acid. Cancel the 2 electrons here, becomes 2 Pb2 plus H2O. And what's the E cell? Equals to this plus this. So here's 2 carry 1 is going to 8.1 positive. But it's not 2, is it? No, it's 1.82. So how do I increase this voltage here to 2? So what they do is they add sulfuric acid here. Okay? They put H2SO4. Why? Because Pb2 plus here, well, this one here, I'm going to put red color so you can see the difference, okay? Because the Pb2 plus here, well, will then react with P2 plus here. Once it comes out, you react with your SO4 2 minus 2 to come out PbSO4 quickly, no? So this one will decrease. The concentration of this one will decrease. What happens? Equilibrium will shift what? Shift forward, no? Okay? Equilibrium will shift forward. And the shift forward, what happens to this one? Become more positive, becomes more positive to reach 2.00 volts. That's why you add the one. They ask you. Now, let's look at here. I got here. I've got the whole thing here. Okay? Right. See. When H2SO4 present, it becomes this one here. Okay? So equilibrium, when this shift over here, when this one decreases, right? Yeah. When this one goes down, right, equilibrium shift forward. Okay, so now here you can see here, right? You put PbSO here with the SO4, right? With the P2+, it comes on here, and this one will increase, push it forward. From what? From originally 0.13 to 0.356 positive. So it's positive 1.47 to positive 6.5. So the whole thing is increased. Got it? Okay, and let's see how it comes out. Okay, we call it something later. It comes out in this way. Let me show you how it comes out. Okay, I did it here. All right, now here. Right, this is what year was it? This is 2010. So in cells of lead acid car battery, the following reaction takes place. They give you the thing here, right? Okay, this ox. Actually, I hate to say that they are wrong or whatever, but you know, you see, normally, put blue lah. Normally, anode means oxidation. Normally, you look at any book, see, but here's reduction. You see, okay, so never mind. You take them as correct. Cathode means what? Reduction. Okay, so check any book, it's true. Okay, so this should be this is oxidation. Okay, so this should be called anode. This should be called cathode. Okay, so just in case you are so trained in your thinking, never mind. All right, so here, remember, this goes this way. Use the data booklet to find the E cell. Very simple. That means in this case, you follow here. You don't use this one here. E, okay? You can use that. Okay, reduction minus E oxidation. You can use if you are careful. So this one go this way. Now look at it carefully here. All right. Remember, what give you is this way, isn't it? Okay. Okay, now this way. So you can see here, PB. I will aim at this, okay? I don't take so much time. PB, where's PB? Couldn't PB. Okay. PB to PB, here to be, okay, this way, isn't it? So it's positive 1.3, okay? So here is positive 1.3. It's positive 1.30, okay? Now this one here, PbO2 plus electron here, will give you what? Give you, of course. Okay, I'm going this way. So it's positive 1.47, positive 1.47. Okay. Okay, so data booklet, simple. So what is this? It's positive 1.77 volts. Okay, accordingly, that's not. So constant equation for this overall, very simple. Just cancel, just add lah. Okay, PB, include the states, since they put the states, PbO2 solid. Okay, cancel this one here. I say I put the plus 4H plus here to give you equals, right? Give P this 2 is here, 2 Pb2 plus 2H2O liquid. Okay, this equals here. All right, let's see whether I got the answer here. Okay. Right here, okay, right? 1.6 positive 1.6 positive. How come different now? 1.30. So 0.3. I say. Sorry now. This one is 0.30. See, hurry. Let's check again now. Check it right. So I've got something wrong here. 0.13 lah. I'm sorry. 0.13 is 0.13. Correct. So here I'm wrong here. So see, so yeah, haze mixed waste. I gotta go now one. So plus 1.60 volts. Okay, it's correct here. Right? 1.60 mark. Okay. So now this equation, okay, right? Another mark here. Okay, so if the electrolyte in the lead cell is it's not H2SO4. All right, so most of the Pb2+ are produced and are precipitated as highly insoluble. Okay, constant equation for the overall reaction in the presence. That means here you must put down here. So this one here, remember 4, right? 4 here, All right, which means that this must be in your red color H2SO4. So this is why you see to prepare is better than H2SO4. So how to get 4 times 2 now? Okay, SO4 here, isn't it? So you put PB, and so you did some training, you know, PbO2 solid plus put down 2H2SO4 equals, okay, now to balance off. Now here will be 2 what? PbSO4, isn't it? See, 2 SO4 plus, of course, 2H2. So this is the overall equation. See, 2 moles of sulfuric acid. You can see it. See? Right, you can put right there. See? Or, see, if you join together, it's 2 moles of H2SO4. Okay? Do they want ionic or what? I forgot to see. Overall cell, don't get overall cell reaction. Okay? So by considering the effect of decreasing Pb2 plus on the electric potentials of the cathode and anode, you know, why cathode and anode? Because both of them produces a Pb2 plus. So you reduce this one here, reduce the effect on the presence of the sun here, which means that it will increase, right? So this cell will increase, right? Will increase. Why? Why? Because Pb2 plus here will decrease, will shift what? Equilibrium position will shift, I'm going to hurry, will shift where? Forward to the right. Okay, right, become more positive. See, okay? Pb2 plus decrease, right? It will increase, right? Become more positive, okay? Right? So it will decrease, okay? Now here you see, see it, this is very good. See? It will decrease, that means it will shift forward. Some will become more positive. I know. Some will become more negative. More negative, minus become positive. See? Sun here, right? Sun here, right? Okay, because here, actually sun is, see how the answer is very good. She's one thing, this is PB. It's just let you know, see why you answer that, minus 0.13. Okay? Okay, right? Now, when this decrease, when this decrease because of PbSO4 form, right, it will shift backwards now. It will shift backwards. It means that it become more negative then, more negative, right now, which will make it more positive when you just minus now. Okay. Now this one here, when you decrease this one here, you shift forward. It means this one becomes more positive. See, more negative, more positive. See, that's what I see here. So go and think about it. There's some time. So the E electrode for Pb becomes more negative, correct? Right? PbO4 becomes more positive. Because this one here, right, will be this one here minus this one here. More negative now. Okay. Okay? All right. Now I won't go some more. All this I will just count with more later. So next time we do, of course, is electrolysis already, right? They are on good state. I'll cover a bit more of those kind of cells, iodine, whatever, rechargeable cells, and for next week we'll continue, okay? All right. Bye then, see you.